Bismillahirrahmanirrahim. Good day everyone. Alhamdulillah. Now we are on example 5.7, okay, where we have here one block pushes another, right? So two blocks of masses M1 and M2 with M1 is bigger than M2 are placed in contact with each other on a frictionless horizontal surface as in the figure. A constant horizontal force F is applied to M1 as shown. Right? A. Find the magnitude of the acceleration of the system. So we can predict that the whole system going to move in this direction with certain amount of acceleration. Bear in mind the one that has a direct contact with the F applied is M1. Right. So if we want to have the acceleration, we can make this or treat these two blocks, okay, or object become a system. Okay, so find the magnitude of the acceleration of the system. So when we talk about system, means that we combine these two M. So sum of F according to Newton's second law equivalent to MA. Okay, and of course the motion is along x-axis. Right, so the M that we have for a system according to this figure is a combination of M1 and M2, okay, directly times with the A. So from here we can determine the A equivalent to F over M1 plus M2. Right, so part B, determine the magnitude of the contact force between the two blocks. Okay, so remember we applied directly F onto object 1. Okay, since object 2 is just next to object 1, so this object 2 going to be pushed by object 1. Okay, so blue block here going to experience P12 1, okay, on 2, so it will be pushed to the right. Okay, so according to the Newton third law, action reaction, all right, when there is a push here, must be reaction from blue block or M2 to M1. So this block M2 going to react, okay, so it's going to push back, okay, in opposite direction but same magnitude, just that opposite direction and acting on different object, okay, acting on M1 because M2 is pushing back M1. So if we list down all the forces acting on object 1 or M1, we have applied force to the right, we have pushback reaction from M2 to the left, and we have weight to the center of the earth, and we have normal one because block 1 here is placed on the table or floor. So there is a contact, must be normal force. Okay, then now consider object 2. What we have here, okay, is a push from object 1 on object 2 to the right. We have weight. We also have normal 2. Normal 2 due to the contact between object 2 and the floor or table. Okay, so this is all the forces acting on these two objects, right? From there, we are going to continue to analysis object 2. Okay, so what we have here, we know all the time, bear in mind that the whole system, both of the object going to move to the right with A amount along X. Then, sum of F along X must equivalent to MAX. Right, so the only force that exists along X-axis is P12 equivalent to M2AX. So if we want to determine the A now, we may rearrange this equation, okay, into this, where we are going to use the first information in part A just now, AX equivalent to F over M1 plus M2, and now we have another information, P12 equivalent to M2AX. So the A here, substitute it here, right? Then you will have this equation to determine F12. It seems like kind of tough because you don't have the values, right? Don't worry. Okay, during exercise in our class, we are going to use the example or the exercise question that has value so that you can appreciate it more. Now, object 1. Okay, so this is all the forces acting on it. Summation of fx, okay, is equivalent to f to the right, positive. When we do summation, we actually doing the addition process. Supposedly, summation of fx equivalent to f plus actually. But P21 is to the left. So it has negative sign. Right. Equivalent to M1A along X. Right. So it is simplified to be like this. Okay. Then we rearrange for our interest, which is P21. P21 is equivalent to M1AX. Okay. Negative actually, yeah. Let me put it like this. From here, negative P 1, 2, okay, is equivalent to M1AX, right, minus F. Eliminate the negative, both sides. You have to multiply with negative 1, right? So you will have this kind of. Okay, so the AX here, okay, again, you're going to take it from the part A. Okay, substitute it here. Then you will have this as your P12. Actually, it's the same, isn't it? Yeah, it's the same. So it doesn't matter whether you're going to use object 1 or object 2. You will get the same answer for P12. This is as a proof that P, magnitude of P12 is the same to the magnitude of P21. Now, imagine that the force is applied toward the left on the right-hand block of M2. Is the magnitude of the P12 the same as it was when the force was applied to the right on M1? So now, if now we are pushing M2, okay, to the left, okay, so we want to determine whether the magnitude of P12, okay, is the same or not when we apply to the M1, F to the M1, okay, to the right in terms of direction. So imagine that now, okay, we are going to redo all over again, okay, the whole part of the calculation just now. Analysis one by one, just like step A and step B. Okay, from step A, you are going to figure out the AX equivalent to what. From step B, you're going to part B then, you're going to determine P12. Or you could also determine P21, magnitude of it. Either you're considering object 1 or object 2, doesn't matter. It will give you this answer. Right? When you have this answer, okay, if you compare to the previous one, here, okay, this one is M2 over M1 plus M2, right? But then, for this case, it's M1 over M1 plus M2. Slightly different. Okay, here is a different. Since, okay, we know that M1 is bigger than M2, greater than M2, okay, so what will happen if this one is bigger amount? Okay, of course, okay, what will happen? The P12 also going to be bigger in amount or greater. Right? That is the answer. Then now, example 5.8. A person weighs a fish of mass M on a spring scale. attached to the ceiling of an elevator as illustrated in the figure. Show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. My dear, actually this is also known as apparent weight situation. Okay. So if let's say we are considering first thing first, the true reading or the true weight of the fish, okay, so means that the whole system is not in motion yet. So if that the case, then we are going to have sum of Fy equivalent to MA, and the A is 0 because it is not in motion yet. So what we have here is T upward minus weight. Okay, this is the original situation of the fish. You have tension upward, you have weight downward, and it is not in motion. So simply we know that T is equivalent to mg or Fg. This is, so if it is moving upward, we have T upward, we have Fg downward, and we have A upward. Okay, so always remember our setting: upward as positive y, to the right of as positive x. So from here, if we do summation of Fy, okay, you have what kind of F along y? You have positive T plus of negative weight because it's downward. It's equivalent to MA, and our A here along y, right? So from here, the reading, okay, of the scale is the T. Okay, so you have MA, okay, plus Fg. So means that the reading on the scale gonna be slightly bigger from the true reading. Okay, because you have to add up MA, right? So from there, okay, we may substitute Fg equivalent to mg to simplify the formula. Okay, so from there, m is collect outside. Okay, if we want to put the mg outside, mg, okay, times with the ay over g plus 1, right? So means that we can see that the T, the reading of the scale, the weighing scale, slightly bigger because you have to add up the factor of this, right? Let's say the object is moving, the elevator is moving downward. You have Fg downward, you have tension upward, and now the A is downward. Okay, for this case, right, we are going to do summation of F equivalent to MA along Y. Okay, where we have now, okay, T is positive, okay, plus negative of Fg, alright, equivalent to M, but our A right now is along or pointing to the negative Y, right? So we're going to have, okay, Fg minus MA. Alright, so what does that mean? What does that mean? If this case you have T equivalent to MA plus mg, okay, so here we have mg minus MA. It means that whenever elevator is moving downward, right, the apparent weight, the T, the reading, okay, of the weighing scale will be less. Okay, so seems like, okay, it's lighter, the weight of it is smaller. Okay, that is why we call it apparent weight. It's not the true weight. Apparently, okay, it's less. Okay, less weight. Apparently, it's bigger amount in weight. Right? So that is how to do the analysis for apparent weight like this. Right, B. Evaluate the reading for 40 Newton fish if the elevators move with an acceleration of AY, positive or negative, 2 meter per second squared. So let's begin with positive 2. So from the formula that we derived already just now, okay, T is equivalent to weight, okay, the FG, right, the A, okay, over the G plus 1, right? So from this equation, we will get the amount is 48.2 Newton. As we know, okay, this is actually not the true reading of the weight. This is apparent weight. Now, if we use negative 2 moving downward, okay, meter per second squared of the A, so we are going to see the reading of the T will be 31.8 Newton. Apparently less, right? Suppose the woman in the figure tires of watching the scale and exits the elevator. Then the elevator cable breaks, mashallah, and the elevator and its remaining contents are in free fall. So now, when you have a keyword of in free fall, it means that the AY is equivalent to the G along G. What happened to the reading of the scale? Okay. So as we know, T equivalent to FG AY over G plus 1. Okay. From here, the AY now we are going to substitute according to the direction of the G, which is downward. So if you see here, this is going to be 0. Right, what does that mean? Because it's free fall, there is no more reading of the weight. Okay, the whole system is falling apart. Right, no reading on the scale anymore. Now we move to example 5.9, the Atwood machine. When two objects of unequal mass are hung vertically over a frictionless pulley of negligible mass, as in the figure, the arrangement is called Atwood machine. The device is sometimes used in the laboratory to determine the value of G by measuring the acceleration of the objects, determine the magnitude of the acceleration of the two objects, and the tension in the lightweight string. Okay, so the string must be unstretchable, lightweight, and the pulley must be frictionless. This is important, okay, to make sure the T along the rope or the string is the same everywhere. So the T experienced by this in terms of a magnitude is the same to the T experienced by M2 here. So sum of Fy equivalent to T minus M1G equivalent to M1A. For which object here? Of course, for the first object. So the forces acting on this object, you have tension upward. Okay, tension always away from the object being considered. Remember that. And then minus the weight of object 1. Okay, to the respect of object 2, okay, tension also away from the object. So the tension is here. Okay, so this is the T experienced by the second object. This is a T experienced by the first object. The T is the same, right, in terms of magnitude. So now, this is for M1. This is for M2. Now, combining the T. Okay, we have here, rearrange first. T is equivalent to M1 AY plus M1G, right? Here we have T is equivalent to M2 AY minus M2G. Rearrange this one firstly. T, you have M2G minus M2A, right? If the T is the same, equate. Equation 1 and equation 2. So you're going to have m1 ay plus m1g equivalent to m2g minus m2 ay. So collect the same item, okay, at the same side. M1g minus m2g equivalent to negative m2ay minus m1ay. Okay, so if you want to make it positive this side, then both sides you have to multiply with negative 1. Then you're going to have m1g plus m2g equivalent to positive of m2ay, okay, plus m1ay. Alright, so this is similar to this one. Okay, so rearrange depending on which item that you are interested in. The A, right? So from them, if you refer to this, okay, you rearrange for the AY, you will get this amount, right? This is in terms of formula for AY. Okay then. Describe the motion of the system if the two objects have equal masses, that is M1 exactly equals to M2. If M1 equivalent to M2, okay, supposedly we know it's balanced, okay, means that no acceleration. Then how to prove this? Okay, you substitute to A equation, M1 equivalent to M2. What will happen to this? 0, right? Which give you, again, 0. It proves that, okay, both of the object are balanced and should be no acceleration take place. Right. What if one of the masses is much larger than the other? Let's say M1 way bigger than M2. Okay, so again, back to the equation of AY. Okay, logically, okay, from AY here, we see M2 is way smaller, M1 is way bigger. So mean that this whole part of this equation more or less too can be simplified to M1 over M1, right? Because M2 is too small, let's say 20 gram compared to 20 kilogram. The 20 gram has no effect actually to the equation. That is why the formula simplified to this. This is the meaning of this assumption. So you will get negative G. What does that mean? Okay. M1 going to fall according to free fall case, okay, freely, as the M2 were not there because it has no effect. Alright. Okay, 5.10, acceleration of two objects connected by a cord. Okay, a ball of M1 and a block of M2 are attached by a lightweight cord that passes over a frictionless pulley of negligible mass as in the top figure here. Okay, the block lies on a frictionless incline on angle of theta. Find the magnitude of the acceleration of the two objects and the tension in the cord. So again, remember when we talk about tension to the respect of this object, the tension is away from it, and the tension of this must be away from it. Right, so object 1, okay, is moving upward. Okay, if according to the diagram given, it is already given information to us where should the A, okay, going to be. So, okay, for the M1, you have weight, you have tension upward, you have acceleration upward as well. Don't forget that. The A. Okay, and then for object 2, you have weight. Let's Let me list down. Okay, you have normal, you have weight. Weight here, M2G. Okay, you have tension to the left, you have A to the right, let's say. Okay, selecting this setting axis will be better for us because we don't have to resolve many forces, only one force, which is the weight, to be resolved. Okay, and we can prove that this theta is the same to this theta. Okay, so this will be the free body diagram for M2. From there, let's analyze. Now, alright, summation of Fy equivalent to T, positive, upward, minus Mg is equivalent. This is wrong. Supposedly, T upward minus M1G equivalent to, is moving upward, right? M1A. Right, so from here, then you're going to have T equivalent to M1A plus M1G. Then you can have this one. Right. For the M2, now, summation of F along X prime. Okay, this is a setting axis now, yeah? Slightly different compared to the first one. It's M2G sin theta. What is M2G sin theta? The component of the M2G. Okay, you have this. Okay, you also can imagine it is here. So this is also M2G sin theta. Right? So it's X component. Okay, pointing to the right, to the positive X prime. And then minus T pointing to the negative X prime. Okay, equivalent to M2AX prime. Right? Or simply M2A. Right? Then summation of along Fy prime equivalent to normal minus M2G cos theta equivalent to 0. Why is it cos here? Because this component to the respect of this angle is actually adjacent side. That is why we are using cos. Why is it here is sin theta? Because to the respect of this angle, this is opposite side. That is why we are using sin theta. Right. So from there, okay, we can rearrange our interest. Okay, along y there is no motion, yeah, so the ay is 0. Okay, then you have here is mg2 sin theta minus t. The t is coming from the first object just now, m1g plus a equivalent to m2a. Simultaneously solve here. Then if you have the value, you may substitute and solve it. Right, so in terms of equation, if you are interested in A, this is the equation will be from here, yeah. Okay, if you are interested in T, then you don't have to substitute, you in other way round. Okay, then you will get this one. Play around. Right, what happens in this situation if the theta is 90 degree? Okay, if the theta is 90 degree, it become a Atwood's machine. Oh, why? Yeah, if the theta is 90 degree, you have pulley. Okay, right? And then you have object 1 and object 2. Right, so this is a kind of Atwood machine. Then, how to prove this? This equation, you substitute the theta here, 90 degree. So, sin 90 equivalent to 1. right? So the equation going to be simplified to this, which is this Atwood machine, right? So again, you substitute theta here 90 degree, you will simplify the formula for T into this, and again, this is a kind of Atwood machine's formula. What if M1 is 0? Okay. If the M1 is 0, okay, describe a mass sliding down a frictionless inclined plane similar to the sliding car problem. Okay, so what does that mean? Well, it means that the A now, okay, substitute the form, the M1 is 0, you will get exactly the same to the equation of the problem of the sliding car. But my dear, do not memorize the formula. You have to derive it from the beginning, from the base understanding, based on your understanding on the situation, and always apply with the step of free body diagram followed by the Newton second law analysis. Now 5.8, forces of friction. Friction is a kind of force that created by Allah Ta'ala, so that this force going to against any other force that going to cause motion. So if you refer to this figure, okay, there is an applied force F to the right. Okay, so frictional force, since the dustbin here is still not in motion, so frictional force here is static frictional force, going to be in opposite direction to the applied force that may cause the object going to move. So it depends on the type of the touching surface, how big the area is, the material of the objects as well. Okay, so all of this contribute to the amount of the frictional force. Spin, let's say, sitting on the floor without any force. In this situation, okay, this object going to have weight and normal only. Okay, since there is no applied force, there is no possibility or tendency to move. Therefore, there is no friction. But the moment you apply a force, okay, let's say you pull it here with certain amount of F applied to the right, so the tendency to move is actually to the right, isn't it? It's possible to move, not yet in motion. Okay, it's possible to move to the right because we are applying some amount of force to the object. Okay, so if it is possible to move to the right, then okay, frictional force. Okay, according to this. So whenever there is no motion yet, this frictional force is known as static frictional force. Right. So the bigger the amount applied force here, the bigger the amount, okay, frictional force to the left, because the purpose of this is to against the F, right? Until it reach one maximum value, okay, then the object on the verge to move is going to move, okay, according to this graph. Frictional force is equivalent to mu n. So this is the general equation. This is a constant coefficient of frictional force. So in general, frictional force equivalent to mu n. This is a coefficient. This is a normal force. So since we have two types of, okay, static and kinetic frictional force, therefore we may write the equation in terms of mu s n or mu k n. The object already in motion, then the static frictional force just now becomes or change into kinetic frictional force. So within this proportionality region, we call it static region, means that the object is not yet in motion. Here now, the object already in motion, the value of Fk remain the same throughout the motion. And always the Fk is less than Fs maximum. Okay, so this is the value of coefficient of friction. Okay, the highest of it is 1.00000. Okay, because it's actually a ratio. If you rearrange this equation, right, regardless whether it's fk of fs, f over n is equivalent to mu. It's a kind of ratio. When you do ratio, force over force, you have no units, one thing. And the biggest amount for ratio must be 1.00. Okay, this is between rubber and concrete. It means that confirm the object won't move at all. Okay, won't possibly in motion, right? For static region here. Okay, for static mu. Okay, so the rest will be less lah, even less. Okay, example 5.11, experimental determination of mu s and mu k. The following is a simple method of measuring coefficient of friction. Suppose a block is placed on a rough surface inclined relative to the horizontal as shown in the figure. The inclined angle is increased until the block starts to move. Show that you can obtain mu s by measuring the critical angle at which the slipping just occurs. Okay, so this object placed on the incline with a rough surface, so confirm there is a friction. So what will happen to the block? It is possible for this block going to slide down. So possible motion is sliding down. Okay, this is possible motion, right? So means that friction going to be opposite of it. Okay, it's going to be this direction. And this block has normal force, has weight. And this is a component of the weight, okay? Mg sin theta, mg cos theta. Then, according to this diagram, now we are going to do summation of fx equivalent to ma, but a is 0 because it is not in motion yet. Alright, so we set this is our x-axis and here will be our y-axis. So what we have here, we have mg sin theta to the direction of x. So it's positive, plus actually, but negative of fs. Why is it s? Why is it s? Because still the object is not in motion, so it's still static frictional force. Right, then along y, okay, we have normal minus mg cos theta is also equivalent to 0 because there is no motion along y as well. So from here, to determine fs is equivalent to mg sin theta. And to have mg, it's coming from y component. Mg is equivalent to n over cos theta. So if you substitute it here, you may simplify sine over cos is tangent theta. So again, okay, what is fs? Recall back, fs is mu sn equivalent to n tangent theta. So now if it is on verge to move, slipping, then theta here known as critical angle. So you can cancel out the n here, then you are left with mu s is tangent theta c. So angle has no dimension, remember? So means that mu s has no dimension. It has no units because it's a kind of ratio. Right, 5.12, the sliding hockey park. A hockey park on a frozen pond is given an initial speed of 20 meter per second. If the park always remains on the ice and slides 115 meter before coming to rest, okay, determine the coefficient of kinetic friction between the park and ice. Okay, so now if let's say, okay, this is the hockey park and the possible motion is to the right, so friction going to be to the left. So since the park itself already given initial speed of 20 meter per second, okay, so now it confirm you have a motion and you have another information of 115 meter before coming to rest. So this is the displacement travel or distance traveled by the hockey park. So list down all the forces acting on the hockey puck. We have normal force, we have weight, we have friction in opposite direction to the motion. So summation of Fx equivalent to MA, but the only force that exists along X is the Fk. Negative of Fk because it's pointing to the left, as according to our setting axis here, to the right as positive X, upward as positive Y. So that is why you put negative sign here, equivalent to MA, X. Sum of Fy, okay, equivalent to normal minus weight, equivalent to 0 because there is no motion along Y at all. Then you have to rearrange this formula, substitute Fk with the mu Kn. Okay, mu Kn is equivalent to, okay, what is your N? Your N is coming from here. Your N is equivalent to mg. So substitute it here. Right, then you have equivalent to MA. From that, you can cancel out the M. Then you will have A is equivalent to negative mu K G. Right, so in terms of mu K, to prove to you that it's a kind of ratio, is negative AX over G. Okay, and don't forget that G is, this is a kind of acceleration, this is a kind of acceleration. So it's a ratio. Then now, right, from here just now, another information that we have in our hand is about 115 meter. That is about kinematics, right? So we are going to use, okay, V squared, Vx final squared, equivalent to Vx initial squared, plus 2ax delta x. So, okay, finally it becomes stop. So this one, 0. Okay, initial speed given to us, right? We do have this information. Okay, and then our A is coming from here. We can put it here. Our x final is 115. Our x initial is 0. So your formula going to be simplified in terms of this. Now, okay, you will simplify this version of formula to figure out your mu K. Okay. If you substitute the value, okay, with 20 meter per second squared, and the G is 9.8, and your X final is 115, you will get the value of your mu K is 0.177. Okay, last one. Example 5.13, acceleration of two connected objects when friction is present. Okay, a block of MM2 on a rough horizontal surface is connected to a ball of M1, okay, by a lightweight cord over a lightweight frictionless pulley as shown in the figure. A force of magnitude F, okay, at an angle of theta with the horizontal is applied to the block as shown. And the block slides to the right. Okay, so the whole thing is going to move to the right. The coefficient of kinetic friction between the block and surface is mu K. Determine the magnitude of the acceleration of the two objects. Right, so free body diagram firstly, for the hanging object M1, you have tension upward, you have weight downward. Don't forget that your acceleration is upward. Okay. Then for the second object, okay, you have normal, you have weight, you have this F, resolve it to the components, you have F sine theta, you have F cos theta, you have friction because the motion is to the right, okay, the possible motion. So friction going to be to the left, and we know that there is a tension away, so pointing to the left as well, to the respect of M2. So for M1, summation of Fy equivalent to positive T minus M1G equivalent to M1A, upward positive. For object 2, summation of Fx, okay, equivalent to our setting as usual. This is positive X. So fx equivalent to f cos theta minus fk minus t equivalent to m2 ax, right? Then our a is completely along x. Summation of fy, okay, equivalent to 0 because there is no ay, no motion along y component. So what we have along y component, you have f sine theta positive, you have normal positive, you have weight negative because it's pointing downward, equivalent to 0. From here you may reduce to rearrange it to have n. So then from that, okay, you substitute your fk with mu n, and your n is this one, right? Followed by, okay, the fk you have in this equation, okay. So rearrange this equation, okay, or you substitute your fk here with this one, right? You substitute your fk here with this one. So this equation going to be like this, okay. Then rearrange, as our interest is a, rearrange the equation. This will be the equation for the acceleration, right? So Islamic scholars, okay, we have lots of Islamic scholars actually besides the Westerner scientists. We have Hibat Allah Abu Barakat al-Baghdadi, born in the Nathanael, Iraqi of Baghdad, stated that constant force imparts constant acceleration. So constant force impart constant acceleration. So it's similar to the net force is equivalent to ma. According to the slow-mo find, al-Baghdadi's theory of motion was the oldest negation of Aristotle's fundamental dynamic law, namely that a constant force produces a uniform motion. So it's even older compared to the Aristotle, not to mention about Newton's. This is way before Aristotle, okay. And it's thus an anticipation in a vague fashion of the fundamental law of classical mechanics, namely that a force applied continuously produces acceleration. The same century, Ibn Majah proposed that for every force there is always a reaction force. It is Newton's third law. While he did not specify that these forces be equals, it is still an early version of the third law of motion, which state that for every action there is an equal and opposite reaction. So actually Muslims are very, very intelligent, okay. So be proud of our Muslim scholars. Okay, this is another one, Al-Jazari, okay, water device in 12th century. So it's about balance. It's about net force and balance, okay, until Al-Jazari be able to create, okay, such a good invention without any electrical devices or pump, okay. This is only completely solely mechanical. That's all from me. Thank you very much for watching. Inshallah, we will continue to the exercise, okay, with all values so that you can understand more, inshallah. Assalamu alaikum.